All right, hey everyone, today we're just gonna talk about mixers, and then we're gonna wrap it up with some filters, and add one more kind of piece to the puzzle. Okay, so before we talk about this, let's just quickly talk about why we need a mixer. Okay, so first we started rapid saying, okay, we have this hardware system, we know we have to deal with frequencies, how do we generate frequencies, like do we have an oscillator, how do we amplify them, have an amplifier, and we have something called a buffer, which is just, buffer stones. So that's all good, but next we want to figure out, okay, how do we go up in frequency? And we do this for several reasons. The first is, we could stay at like 1 megahertz if we wanted to, and broadcast at that. But at 1 megahertz, you need an antenna that's like twice the size of this room. So it's not very feasible. So in communication systems, you upconvert frequencies, you have a smaller antenna. So what happens is your antenna length is generally going to be proportional to your frequency, so just your wavelength. Right, so higher in frequency means your wavelength goes down, means your antenna length goes down as well. So for example, your phones, you have a very tiny antenna, right? So you can kind of estimate maybe you have something operating in the gigahertz range, which is in fact what it is. You'll have Wi-Fi 2.4 gigahertz, 5 gigahertz, Bluetooth at like 1.8, I believe, stuff like that. So this is one relationship as to why we want to go up in frequency from 1 megahertz to 27, which is where we're allowed to broadcast by the FCC. So our goal is 27 megahertz, and we have to get out there somehow. And we do so by something called a mixer. And as for what that is, how it works, we're going to get to. But the basics of a mixer are as follows. I'm going to do this slightly, I guess, backwards. I'll first do the general theory behind a mixer, and then talk about the specific mixer that we're going to use. Okay. So let's say we have a signal. Let's call it x of t, and we have some switch it's connected to, and then some load, and some output voltage, right? And then what we do is we say, okay, if this switch is on, then what can we say? We can say that V out is equal to x of t. Our output is our input. And for clarity, I'm just going to call this V in. Okay? If the switch is off, V out is just left floating. Okay? So now let's say we flip the switch on and off at a certain frequency. Let's say we have this hooked up to some signal we call VLO. So LO, if you remember, is like local oscillator. And let's say our VLO looks like a square wave. And for simplicity, we're going to assume a 50% duty cycle. So it goes on, and it goes off, and if this is this whole period is t, this is going to be t over 2. So 50% duty cycle. As for why we like 50, it's a bit more complicated, but for the time being, assume it's on half the time, off the other half the time, okay? So we can construct a few things from this now, and what we want to do now is we have this square wave that's controlling what our V out is equal to. When it's on, V out is V in, when it's off, V out is left floating. And it switches at this frequency here of our LO frequency. Okay, so if you notice, you're kind of incorporating some input signal, our LO from like our oscillators before, and then we expect V out to have some frequency too. All right, the question is, well, how? So what happens here is we can simulate this as follows, that V out, I'll use time notation here, is going to be equal to V in of t times some square wave of t. This kind of follows, right? You can just make this approximation, say, okay, it's on, it's connected, it's off, there's nothing there. This follows, right? if we look at a square wave, can anyone tell me, I guess from like 102, what a square wave is? Think in terms of a simple sinusoid. Any thoughts?
Jumbled up frequencies of sinusoids.
Exactly. There's some pattern to it, right?
Yeah.
You have the fundamental, then you have the third harmonic, the fifth harmonic, etc. So I'll try and describe this. This would be like the first harmonic, your fundamental. And then your second is probably, sorry, your third rather, it's going to be, let's see. This. Something like that. So we can express a square wave in terms of fundamental frequency, third harmonic, fifth harmonic, so forth. Okay? So from there, what we can say is if our Vin has like a certain frequency, right? Let's say this is like omega naught, right? And the square wave has its fundamental frequency. We can say this is like omega LO1, but it also has other components, right? It has like an omega LO3, omega LO5, so forth, all the way to infinity, right? So we can see that we have omega naught times omega LO1, and then omega naught times omega LO3. So we have these like mixing between these frequencies. And if we want, we can look at this in the frequency domain as well. But first, I just want to draw one more diagram for you before we get into that. So this is what like an ideal mixer is. You have like this switch. You want to draw it as far as like a schematic diagram goes, right? You have, it looks like this. We have our LO, and we're going to have one signal here and one signal here, right? We have two cases. We can either down convert or up convert, right? So let's say we're going to down convert. We're going to down convert. This is called RF. This is called IF. RF is like your radio frequency. It's the higher one. And your IF is the interfrequency, the intermediate frequency, and this is going to be smaller, right? So you expect for a down conversion case, RF and LO meet, get IF out. And if you're going to up convert, you're going to have an IF here, RF out. This is a typical notation. So I'll write this down as down conversion. Okay. And in up conversion, you just flip these, pretty much. Use the same LO. Okay? So, say we deal with this case here, down conversion. We're going to have some very high frequency RF curve here, and obviously it's one tone, assume one tone. So this is a sinusoid, and then we have our square LO, like this. Okay? Then we have some IF, which is smaller frequency. Right? Looks something like this. This is a top level view of what a mixer does. Any questions so far? Cool. All right. So now I'm going to erase some of this, and we can go into the frequency domain and actually analyze what's happening in this multiplication here. In this time domain, we're saying multiplication, and the frequency, that's convolution, right? So we're going to have a convolution of some omega naught with this sum of omega LO1s,